This next project, well, it's the same project, M11. It's the conveyor system, but this next lab section, if you will, 11B, is probably the most complex code that you're going to write to date and have to understand, because within each rung it is scan dependent, meaning that when you scan a rung, it's top down and then it's left to right. If you within that rung switch some of the branches around, you won't get the same results. So these rungs internally are scan dependent. It's not scan dependent logic between rungs. In other words, if you take and move complete rungs, it's not going to make any difference in how it behaves or operates. But if you try to move the logic around inside of the expression, and if you are done any math or algebra, you know you just can't go moving around parentheses and stuff inside of an algebraic expression and have it come out the same. Not happening. So what we're doing here, in order to give you some experience with that, we come up with an idea to make it easier for you to simulate momentary push buttons. So the start-stop buttons on this system, both for the system and individual conveyors, they're momentary spring-loaded. You press them and release them. You know, close, open, or it's closed and when you push it opens, then you release it, it goes back closed. So it's a momentary contact. But we're not really using I/O yet. We're not going to use actual switches. So that would mean that you would have to toggle the Boolean value from your mouse pointer. But you would have to do it twice. You'd have to toggle it on, then toggle it off, or toggle it off, then back on. The challenge with that is if you're really concentrating on learning and thinking about the logic, and then you go to test it, you may forget. I mean, I do it all the time. Remember, we're using normally closed buttons for stop. Well, when you run the logic, you have to go turn all those on, because remember, the stop buttons are normally closed, which means they're feeding voltage to the screw terminal, so that bit memory is on that represents that input. So if you download and go to run your logic and you haven't gone in and toggled those all on, then your logic's not going to work. It's like somebody's holding down all the stop push buttons. To eliminate that challenge, we came up with some logic that simulates a press and release for both ideas, normally open and normally closed. Now most push buttons, industrial ones, have both contexts, a normally open and a normally closed. But for start push buttons, we use the normally open, and for stop, we use the normally closed. So the logic that you're going to do in this lab is all built around the idea of you going and toggling a start push button, and when you do, that bit goes on and then it turns itself back off. The logic turns it off. You don't have to go in and do a second click. Now, the length of time, and we're using TON instructions. The length of time that we typically use is 200 milliseconds. That's a 1/5 of a second. So that's a real rapid press and release. Most people don't, press and release the button that quick. It's more like press and release. It's more like 500 to 1,000 milliseconds, maybe even a little bit longer. However, if you want to increase the length of that, if you want to call it pulse or depress simulation, pressing the button simulation up to 1 second, 1,000 milliseconds, so you can see the timer accumulating, by all means go ahead and do that. But from a practical standpoint, I just made it 200 milliseconds. But in our discussion, we will describe that challenge. Now, there's the logic for a start push button and a stop push button are different, because one turns the bit on momentarily and the other one turns it off momentarily. So let's get busy and go do this lab. This is how we left our project at the end of part 1. we had 4 rungs of logic in our sequence program. Remember, we have 3 programs: buffer inputs, sequence, and buffer outputs. The logic in buffer inputs and buffer outputs is not part of our actual process program and control. They're simply there to buffer the real I/O to internal bits so we can avoid any asynchronous behavior. Totally unnecessary for this type of a project, but we like to maintain this format and way of thinking throughout our projects, whether they're little like this one or an actual legitimate process to control a machine. We always like to buffer our inputs and outputs. These are the 4 rungs that we have. I noticed that I eliminated some things up here in the menu by going to View and Toolbars and turning off some things. I don't want to turn off the simulator because I need that. And I really don't want to turn off most of this other stuff up here. And I need this work area to be wide enough so I've got the run mode changed. Now, it just occurred to me that I could move this down to here, and that gives me the opportunity to make this a little less wide and not use up so much screen space. In other words, if I'm stuck having a second row here, when I say second row, it's really the 4th row. You have the title bar, you have the main menu, you have some standard menu items, and then you have these items. So I could actually move this down here as well and make it even more narrow. At some point, though, the logic isn't going to collapse anymore. So these are the 4 rungs that we have. We have a system control rung, and then we have 3 conveyors. We pounded on this pretty good. The next thing we're going to move to is how to simulate a momentary start push button and then a momentary stop push button. Now, when you did the labs, maybe you didn't have any trouble remembering to turn things back off or turn things back on after you toggle them. A toggle Boolean is just a straight up change the state from whatever it is. If it's off, make it on. If it's on, make it off. It's not a double like a push button. To press it, release it. We're going to show you that logic. It's called self-extinguishing logic, and I use this logic a lot in real processes because what it allows me to do is to, when a memory location goes true or on, when the memory location goes on, a true if on instruction reads it as true, initiates an action, and the logic itself turns that bit off that we used to turn it on. So I'm going to add that rung of logic. Okay, here's our rung of logic for the momentary, normally open start system push button. And at first it probably looks confusing, and you're going to have to operate it to really fully grasp it. What we're saying is if we toggle on start system push button, rung number 2 goes true and enables the timer. Branching around the timer is a timer not done or true if off timer done, and the timer won't be done for 200 milliseconds, and it turns on start system push button. Now you're probably thinking, well, yeah, but it's already on. That's not the point. There will come a time at the end of 200 milliseconds when start system push button is on and the first instruction is true, rung 2. First, true if on, it's true. The timer has timed out, so the true if off for the Q bit now goes false because it is done, and the false execution of the OTE or the direct coil addressing start system push button turns it off. This is somewhat scan dependent logic. The rung won't work unless it sees that true if on at the head of the rung is true to see that the timer is timed out, and then it does the false execution on start system push button, and the next time it comes around, the last thing it heard was that you're off. So start system push button, that bit memory is off. This is self-extinguishing logic. Might be confusing to look at until you get the full gist of what we're doing. I use this a lot, especially if a condition comes from another source into the controller's database, and the other source sent something to turn it on, and then that was it. It didn't say anything to turn it off. I want to cause something to happen. So you can replace that TON instruction with a whole group of executions, and then the true if off for the Q bit would be when that whole little process is finished, then the false execution turns that bit back off. So it's self-extinguishing. It turns itself off. What we're simulating in this rung, and I put it right after the system enabled rung, we want to momentarily close the contacts of the start system push button. When you toggle it on, the system start pulse timer data type has as its Q bit set to off until the timer's timed out, set to 1 for the length of the preset, which is set to 200 thousandths of a second, thereby simulating the push button being depressed for 0.2 of a second. Or you could say that you toggled it on from your mouse keyboard and the logic toggled it off after 0.2 of a second. You can make that preset anything you want. You don't need to make it longer than it is, because when you toggle it on from the keyboard, that's a 1 scan action. So you could probably reduce that timer preset down to maybe even 1 millisecond. That still work. I didn't experiment with it. You're welcome to. Save and download. Now I can save, but to download I have to start. See, I move my simulator over to here. I have to start the simulator, then I have to turn it on. Now if this path is correct here, this is my wireless adapter. I was using my hardwired Ethernet port. It has a program in it from the last project, which is actually these rungs of logic, but we've added one rung, so we want to download. Do have the simulator running, and we can bring it to the forefront, but we don't need it because we're not using any I/O. These are all internal bits. I have start system push button, start system push button, start system push button. I have it in at least 3 locations. I can toggle any of those. It doesn't matter which one I toggle. But let's toggle the one that we would if we were actually running the system. Let's go up here, right click. Now watch the timer down here. 200 milliseconds might not be enough for us to actually see it function. Didn't see it function. But you see it turn back off by itself. Now I don't think I can bump this up, the preset. Now see, it's grayed out. I can't change this online, so I'm going to have to go to run mode change, and we'll make it 1 second, 1,000 milliseconds to make sure we can see as long as we're changing it. Test changes. Well, this will work out good. We'll test the changes, but we won't accept it. That way we can go back to 200 milliseconds. Okay, so I want to test this. So I'm going to go up here and watch the accumulate down here. So you can see it timing, and it times out. So you can see the logic works. I'll right click here just to show you what I said. It doesn't matter where you toggle the bit, because remember, any place that you see start system push button anywhere in your program, it is addressing the exact same memory location. So if you toggle on it, toggle Boolean value, it's going to have the same effect no matter where you do it. Doesn't matter where it's at in the scan sequence, because you're directly addressing. Here's one that we didn't do. We'll toggle from this one. See, toggle Boolean bit. I am toggling a bit in memory, not the instruction. So it doesn't matter where I toggle it. Anywhere I see it, I can toggle it. Self-extinguishing logic. Now this is the start push button. And it works good. Now we're not going to end up leaving this rung in with our real conveyor control rungs, because this is simulating something, an actual hardware push button. Normally open push button. We press it, input goes on, we release it, input goes off. And we're doing it for here 1 second, but we're going to leave it at 200 milliseconds. So I'm going to go up here and I'm going to discard unaccepted changes. And see, there we are back at 200 milliseconds. So if we go up here, operate our start button. So you never see this change because only accumulates from 0 to 200 milliseconds. That's 1/5 of a second. Let's save and go offline. Save. Now let's add another rung of logic for our stop push button. I see there was a question in the manual when we got done playing with the logic, and that is, you will have to observe quickly for some of this execution of logic. The next step will demonstrate that anywhere that you see an instruction with a memory location of interest will do for toggling the bit. How many locations are there in the logic where the start system push button is used? We already said that, kind of 3. I just want to make sure you got something to fill in the blank. And then you should probably toggle all 3 just for your own edification. Now remember that the action of a normally closed push button, like the stop button, has the exact opposite sequence as a normally open button, like the start button. So the stop button is on, And when we toggle it, we want to toggle it off, but then we want it to come back on. And there's several ways to do this. This is the first one. We'll show you another one. We're using the set instruction to turn it on. Now, if it's already on, then right away you should realize that at the top of this rung, you're seeing when the timer times out, stop system pulse.q. When it times out, then it sets the stop system push button back on. That's your first clue. This is what turns it back on after the timer. Right below it, if the stop push button is off, meaning that you toggled it off, then that stays true as long as the rest of this branch here is executing. So when the stop push button goes off in memory, this reads true, starts the timer. The timer's not timed out in the branch around, so it resets that bit. Now, resetting that bit is turning it off. So the second half of this, if you want to say the second and third level, they are keeping it off until the timer times out. And then on the very next scan after the timer has timed out, remember this logic reads from left to right, top to bottom. So the first thing it reads is stop system.q. That's the timer's timed out. That bit is on. This instruction is true. And it sets the stop push button to 1. And then you go down to this next part of the rung, and that's going to be false because the stop system push button is on. That resets the timer and everything else. So this is a little convoluted, but I wanted to use the set and the reset instructions just to give you a little latitude in your perception of what we're doing here. So let's save and download this. Once again, we're probably not going to see any time accumulate, but let's give it a whirl anyway. Stop push button right now is on. That's the way it's supposed to be. And here's what's cool about this. Think about this logic added into your program. What is this logic going to force the stop push button bit to be as soon as you go in the run mode? It's going to turn it on. This rung automatically turns it on. Because if it's not on, then this is true. Starts the timer, and 200 milliseconds later, it turns it on. So let's run this, and we can toggle it anywhere. And you see that it went off and right back on, but you really couldn't see the timer work. So and I could have made it 1,000 milliseconds before I downloaded it, but I really want you to see the run mode change as often as possible so you get used to it. So we'll change this to 1,000 milliseconds, and then we're going to go up and test the changes. Now we'll be able to see the timer accumulate. Let's pick a different one to toggle on here. You can see the timer go on at the end of 1 second. I toggled it off, okay? So here's stop system push button. Let's toggle it off here. I toggle it off, and after 1 second it goes back on. That's all you need. Beautiful. Now let's go up to this rung, because these two rungs right here, we don't want to see these. And by the way, I'm going to go ahead and discard unaccepted changes because I don't want 1,000 milliseconds. See, we're back to 200 milliseconds. So let's go up to our real rung here. I mean, this is what's controlling system enabled. And let's see if they both work. So let's toggle this puppy on. Goes on and back off. Got our system enabled. And let's stop it. Absolutely perfect. Love it. Save and disconnect. In the lab, this is where I had you move all of your local variables to global. So let's go check and make sure that we don't have any local. None there. Oh, got some there. Actually, those could probably stay there, but I had you move them to global. The only way you can lose moving them to global is if you need to use the same tag or variable in multiple programs. Then there would be interference reading them. So I'm going to select them, Control C, go to Global Variables, Control V. Now you see they're in the global variables. Let's go back to Sequence. They're still selected, and hit Delete. And there's none here. So we've cleared out all the local variables, and we'll go ahead and close these local variables. Here's our global variables. Now let's go look at our logic and see if it did what I expected it to do. Notice that this is important for you to understand. If you're going to move variables from global to local or local to global, you're going to run into this problem. And that is that this was associated with a local. So I'm going to have to do them one at a time. Looks like we're good. We also added a new program called push buttons. Programs, add, ladder diagram, and rename it push buttons. Then we had you copy these two rungs out of sequence and paste them in push buttons, and then go back to sequence and delete them. So when we look at sequence, those two rungs are no longer between system enabled rung and the motor conveyor 1 rung. Depending on the sequence that you use to move these two rungs into the new program and move the variables as well if they were in the local, you had to tidy up the little yellow triangles until the logic in push buttons looks just like this, and the logic in sequence looks just like this. Just the 4 rungs, push button. So you see in sequence, there's no local variables. In push buttons, there's no local variables. Here we are in the project, lab project M11, part 2. And in this part of the project, we have removed the simulation of momentary contact push buttons, both for start and stop. We've removed it from sequence and moved it into its own program called push buttons. I had you move those two in there. You're looking at them, start system and stop system, start conveyor and stop conveyor 1. So start conveyor 1, stop conveyor 1. Then I had you duplicate those rungs for the start and the stop. And then eventually we get to a point where I have you put in a new form for the stop. So here's the set and reset. This is the logic that we use for the stop push buttons for conveyors 1, 2, and 3. Then I showed you an alternative not using set and reset, and that's down here at the bottom. And that is, if the input for stop push button is off, then this is true, which means somebody pushed the button, right? The stop conveyor push button is normally closed. Don't get normally closed confused with true if off instructions. They look alike as far as the symbol goes, but that's as far as it goes. That's where the similarity ends. So this very first instruction says if somebody pushed the stop push button, because remember, it's wired normally closed, so when you push it, the input goes off, and when you push it, the input goes off and it starts the timer. Now, I've only got 200 milliseconds in there. You're not going to see that accumulate. You won't see the ET go from 0 and count up to something. It's just not going to happen because it happens too fast for the screen to see it. But the point is, you push the button, the timer starts. Now look right down below. When the stop conveyor 3 pulse is done, at the end of 200 milliseconds, it's going to turn on stop conveyor 3. Now notice it's stop conveyor 3 push button at the beginning of the rung, up at the top, pushing that. This is what we're simulating. Remember, we actually toggle it, but let's say we're pushing it. Then the timer starts, and 200 milliseconds later, it turns stop conveyor 3 push button back on and then seals itself in. So when you put your mouse over here and you toggle this value, you're only toggling it off for one program scan. That's 1/3 of a millisecond at best. Let's just say it's 500 microseconds. So for 500 microseconds, this has changed state. This starts timing, and when it's done, it turns it back on and seals itself in. So if you look at the logic, stop conveyor 3 push button, if it's on, which it would be when you're not pushing the button, then it's turning itself on. Now you're probably thinking, well, if it's on, then how can it turn itself on? Well, the verbs aren't the best to use right there, but it's basically like I always say. In this logic, an OTE, a direct coil, has a true and a false execution. It executes every single program scan. So 3,000 times a second at a minimum, this instruction right here either tells that bit it's on or it's off. That would be like you walking by a light switch on the wall, a toggle switch, a wall plate. And every time you walk by it, you take and you swipe your hand over it. If it's already off and you swipe your hand down, that's in the motion to turn it off, but it was already off, so you might think that's a wasted motion. That's just how these instructions work, because to do it any other way would be a waste of processing time. So you just have to keep in mind, this is scan sensitive. It makes a difference what order this logic is scanned in. So if you flip this all around, then it wouldn't work. This rung would not work if you flip the logic around. It has to see the stop 3 conveyor push button is off first. Then it starts the timer. And as soon as it does, then when the timer's timed out at the end of 200 milliseconds, it turns stop 3 conveyor back on, and then it seals itself in. So let's download this and give this a try. It helps to start the simulator. Sometimes you can get away with this. I am so accustomed to downloading to a live powered up controller that I forget that I'm using the simulator. I design all these labs with a live controller, but I'm doing them all with a simulator to make sure that if that's what you're using, that we don't run into any problems. Okay, so there it is. I'm going to turn it on, and because I didn't turn it on right away, the communications may have timed out trying to do the download. We'll find out. By the way, if you're having trouble with Watchdog timer faults, in the manual we gave you a couple options. One that's popped up more recently is, instead of going to Task Manager and going to the simulator and knocking the number of CPUs down to 2 or 3, do that for CCW in general, and that seems to work better. Now, by the time you watch this lecture, it may no longer be an issue. I'm not faulted. I'm excited about that, and I'm downloading and I'm running. Whoops, I'm not downloading and running. See, I'm looking at this. It looks like I'm good. But when I look here, in other words, this simulator acts just like a real controller out there. It's been running all this time, even though, in a sense, you didn't have it started. When it starts back up exactly the way you left it, just like a real one would be in the field. So now I'm going to say to go ahead and download with project values. Okay, we're looking at the stop. We know the start works. We've tested that a dozen times. This is our new plan for the stop. Now this is a stop up here, stop conveyor 2. This is the logic we were using, toggle it, and you see it goes through. Oh, I saw 31 milliseconds there, so an accumulation did show up, but you see it goes right back to being on, even though I toggle it off here, it goes right back on. That's stop conveyor 2. Let's try stop conveyor 3. Okay, so what you're watching is you want to see this go off and then come back on. Goes off, right back on. Off, right back on. Now see, I did not see this accumulate. So just to verify that this does work, I'm going to go offline, bump up the preset time, and then come back online and try it again. Now you can see it timing out. Now, one thing, remember I said that this is scan dependent. So think about this. Right here at the very first instruction in the rung, I am going to toggle this off. And it's going to stay off for at least one program scan. So during this scan, when I toggle this off right here, that means this is going to be false then. So when I toggle this off, this goes true and that goes false. That's what allows this to drop out, for this to go from on to off, so to speak. Or rather, I should say, that's what keeps this instruction from turning the stop conveyor 3 push button back on, is that when I toggle this off, right there, that went false. And it stayed false because this was off. Remember, we're sealing in the logic here. So this works great. Save and disconnect. What we did for the remainder of part 2 was to test our virtual push buttons, our simulated push buttons. So we went to sequence, and in sequence we have a system enabled rung, then we have three conveyor control rungs. Right now the system is enabled, so I should be able to toggle each of the conveyors. A single click toggles them on, because remember that the logic is toggling those bits back off. So we're simulating a momentary contact. Now, if I hit any of the stop conveyors, let's do 3 because that's the one that we changed the logic up. So I toggle it off and it comes right back on, the button does. In other words, press and release, normally close, push it, goes off, release it, it goes back on in a stop conveyor 3. That was the only thing that we changed from the earlier logic, was in push buttons, we changed this last rung to show you how to use a direct coil instead of set and reset. Now remember, set and reset has its benefits, and if it's all in one rung, I'm okay with it. So I'm okay with this set reset rung because everything stays in one location, and what sets it, the logic that sets it, is contained within the same thought or the same rung that resets it. The problem with latch unlatch, set reset, is that this logic doesn't have to be here. So this true, true, reset, that could be someplace else in the logic. And when you start doing logic like that, where you have the set instruction one place and the reset somewhere else, it becomes confusing and difficult to troubleshoot. So back to our sequence, and let's we still have two conveyors running. We'll just stop the whole thing, right click, toggle. We lose system enabled, that drops out all three rungs. And that's all we did for the rest of the lab, was to test this. And you should test this. Go through and try every possible iteration or nuance that you can think of to see if you can make it not work. It's too simple not to work. Now, the only convolution in the code would be here in the push buttons. But remember, I mean, this is the most complicated code in this whole lab. And it's in here to give you some experience with scan-dependent rungs and with timers, and to think about the execution of these rungs of logic. This is our actual sequence, and that is too simple not to work. So we did ask you some questions. Try toggling on any or all of the conveyor start push buttons. Now, that was when this was in this state. The system was not enabled. And did any of them energize the conveyor motors? No. Did you see the push button flash on momentarily? Yes. In other words, if I went up here, right click here, you see it go red and then back off. So yes, why do the conveyors toggle on or not? They don't go on because you're missing the system enabled. None of the rungs can be true just by pressing the start push buttons. When you toggle the system stop push button in F, did everything stop? Yes, it did. How many push buttons are you simulating in this exercise? Well, 2 per rung, correct? System, start system, stop system push buttons, and then 2 for each conveyor, so 8. And that was pretty much the lab. The last page of the lab goes through a step-by-step sequence of how that direct coil stop push button works, just in case you needed to affirm that. The takeaway here is understanding scan-dependent execution within a rung, and the concept of using logic to undo something that you did. I would not go on until you're sure that you understand how these rungs work. If you go on without doing so, you're never going to use this logic specifically in a practical application with an actual real conveyor or system, because with a real system, you got a real push button, right? You push it, the bit goes on, you release it, the bit goes off, or vice versa. The bit's on, you push it, it goes off, and then it comes back on. So you wouldn't use this kind of logic for push buttons because you have real push buttons, but you will see it for other code when you get into other people's programs at work. We'll see you for the next one.